Okay, the Henderson Hasselbalch equation. I won't ask you to derive it on my exam, but I just want to show you that this expression for Ka is the Henderson Hasselbalch equation, but the Henderson Hasselbalch equation is just a kind of a manipulation of this. So what we do is we want to solve for H30 plus. We rearrange H30 plus is equal to Ka times HA, concentration of HA over concentration of A minus. Rearranging, and then if we take the negative log of both sides, remembering that logarithms have an unusual ability to break up a product into a sum like this. And if this is something that you don't remember, and that's fine. I just want to show that it's nothing new. Now this negative log of H30 plus is pH. Negative log of Ka we call pKa. And then we have, if we flip the acid and the base, then the sign changes on the logarithm. The negative log of anything, the negative log of A would be called, say A would be PA. Negative log of capital X would be PX. Negative log of smiley face would be P smiley face. So anytime you see that negative log of something, it can be converted to that in this context when we're dealing with this kind of math. So this is the Henderson Hasselbalch equation. One restriction, though, is the CA over Ka approximation must hold for the Henderson Hasselbalch equation to work. It's not magic. And we're relying on the fact that that x plus and x minus x and plus x have been removed from these concentrations. If they hadn't been, and that's what we're saying here, we've gotten rid of that minus x and plus x, and so these are just numbers. If we can't do that, then we'd have these two variables as part of the logarithm, and then everything gets out of whack. Now, people will use the Henderson Hasselbalch equation for any system, and when I see that, well, actually in class I most likely will come up with a problem where it won't work, and if you try to use the Henderson Hasselbalch equation, you'll end up with a pH of 35 or something really crazy like that. Let me show you though, the one where it does work. Use the Henderson Hasselbalch equation to determine the pH. So it's a very handy tool, but we just need to know its restrictions. So, and this has HA and A minus, it's base over acid. The pKa, let's see, now we have the Ka for this acetic acid is 1.70 times 10 to the minus 5. So negative log of that is going to be the pKa. And you can see why we use these. We like to have these pKa's, we have pKb's, we have where we use the negative log, because then we end up with a nice simple number rather than a very small number like this. We end up with a large number that's usually between 1 and 10, or 0 and 10, well, 1 and 10. So it's a smaller, it's a nice number to look at. Now the pH then is equal to 4.77 plus the log of the concentration of the base, potassium acetate, there's the acetate, so that is 0.115, over the concentration of the, and we can put the molar in there, over the concentration of the acid, 0.540 molar, and those cancel, and we're left with 4.10. Now, we could have accomplished the same thing doing it the way that we've done it before, using the acid ionization reaction and putting in the values from above. And this is a good check to see. This is minus x plus x plus x. So instead of using the Henderson Hasselbalch equation, we're using the Ka expression, which is just the the expression that we use for Henderson Hasselbalch, we just put it into a different form. So what I'm trying to show is that the Ka expression is the Henderson Hasselbalch equation. They're just two different forms of the same expression. So here's our Ka expression. The Henderson Hasselbalch equation is just manipulating this, but what we do count on is that we get rid of those x's. Now it's just these numbers, and when we solve this, we end up with 0.0000798, and the pH comes up to be 4.10. 4.10, same as here. So the Henderson Hasselbalch is nothing new. It's the same math, except that we don't have to go through the ICE table. We just plug everything directly into this expression. So the first thing is that know that there's nothing new here. It's just a manipulation of the equation we already know. And that the Henderson Hasselbalch only works if the approximation holds, just like we can only get rid of these x's down here for this expression if the approximation holds.